Okay, so this is lecture 26 and this is the last lecture of our semester about the small signal analysis. Um, Actually, I have covered many important discussions in our previous lecture, lecture 25. So therefore, in today's lecture, we will quickly cover some examples taken from my own implementation of small signal analysis. After that, we will just wrap up this semester's entire lectures. So first, I wanted to start voltage excitation at 0 Hertz. So why we have this specialized condition? Is it because we have to consider such a thing round over round t when we consider non-zero frequency? So if we have non-zero frequency, then this operator will be converted into j times omega. So that will introduce a complex number in our matrix. So in order to avoid this complication at the first trial, so I just wanted to set the frequency as exactly 0, then all kinds of time related terms are eliminated. Okay, so then let's say that our goal is to calculate ID versus ID over VD, DI over DV. So in this case, we have to prepare the DC solution, but this is not that difficult to you now. Since it is the solution, the residue vector is a null vector. I mean that when you have the real solution, then when you generate the Jacobian matrix and residue vector, you can find that Jacobian matrix is just given, which is really invertible. However, you will find that residue vector is identically 0. Why? Because this is the definition of your solution. What you have to do is just to evaluate a vector called as a residue, and here all of your entries should vanish. The solution vector which satisfies this condition is called as a solution. So therefore, if it is the solution, then your residue vector should be a null vector. So this is the situation you have for the last DC simulation. When you calculate your last DC Newton iterations. So now for this small signal analysis, please reuse your Jacobian matrix. You can reuse it. Then if you just use this system, solve this system, then you will have nothing because you have 0 or null vector here in the right hand side. So your delta will be also quite close to 0. So that does not introduce any physical meaning. But point is, now you have changed your boundary condition. Especially since we are interested with dI over dV applied to the anode and observing the change of your current at anode. Therefore, you have to change your anode potential boundary condition. Please note that this is the general form of our boundary condition. It simply states that your anode voltage potential, this is not the terminal voltage, but potential, electrostatic potential at a node attached to your anode terminal, then this phi anode simply given by its equilibrium value plus your applied anode voltage. That is written here. Now, let's say that you have the correct solution. So, for example, your V anode can be also decomposed as V anode DC plus your AC perturbation, so excitation here. Then also this solution variable can be decomposed into two parts: your anode voltage but your DC solution, and fluctuation of your anode potential, and that is given by just equilibrium quantity. Please note that there is no term related with, no fluctuating term related with this equilibrium value, because equilibrium value is just an equilibrium value and given number. So whether you make a certain change in your terminal voltage, that does not change this parameter. So you will have also V anode, its DC term, and delta V. That is the full boundary condition. But as we have seen already, so DC term itself satisfies something. What? So DC term itself satisfies this condition. DC solution is given by equilibrium solution plus DC applied bias. So now we can safely eliminate these identically zero parts. Then, simply speaking, we can say that if you apply a certain small signal excitation to your anode voltage, then this anode voltage can be directly affecting the electrostatic potential of that node. That sounds really natural and sounds really reasonable. So now, however, we have no idea about what is this amplitude of delta V. Actually, in this case, since we have already made a certain approximation of smallness of our delta V, therefore asking the exact magnitude of this delta V is really meaningless. So we can say that this small quantity is recognized as just 1. However, what is actually this unit perturbation? Is it 1 millivolt or 10 millivolt or 1 microvolt? That doesn't matter, because this is just a linear system. So if we, for example, if your amplitude is really 1 microvolt, then later, after you calculate all kinds of these quantities, then just multiply 1 microvolt. Then that result will give you the result of applying 1 microvolt amplitude signal to your anode. Okay, so this is normalization. So now, if we adopt this kind of thing, then now our system A times delta equal to something. Previously at DC case, it was just identical null vector. However, now instead of that, now we have a vector whose certain element is 1, and this rho is corresponding to the boundary condition for the anode potential. Otherwise, elsewhere, we have all zero component for our right-hand side vector. Okay? So then, what you have to do is just to solve this system by solving this system, you will get delta, and this delta will contain the information like this. The, the fluctuation of your potential, fluctuation of your electron density, hole density, according to the perturbation applied to your anode potential. So that is the physical meaning of your solution. So now let's have a look at an example of a PN junction. Once again, we consider a PN junction which is biased at 0.5 volt. Then this graph just shows the response of electrostatic potential. So I mean that we are just drawing delta phi as a function of position. And as you can see here, we have value 1 and here we have value 0, because you know this is corresponding to our cathode and this one is corresponding to our anode. Since we have applied unit excitation to the anode, of course anode should have the value of 1. Also, since we have not applied any of voltage fluctuation to the cathode, so therefore cathode should show exactly 0 fluctuation. That is quite normal. And in between we have something, and you can easily understand in this part. So your p-type region, neutral p-type region, there is no potential drop. Also in this part, your neutral n-type region, so there is also no potential drop. Only potential drop can be observed where the central part, which is given as a depletion layer. So now all of additional voltage is just applied to your depletion layer. That is quite normal. Also, please have a look at this second line. The second line means that here we have another one corresponding to a symbol. Yes, there are many symbols here. These symbols are representing the difference between the solution at 0.5 and 0.501 volt. We just introduce 1 millivolt additionally to our 0.5 volt. Then taking the difference. So we have to calculate this difference that is drawn here. Of course, since we have made just 1 millivolt difference, it is not fair to make this difference and our calculated this response, because our response is corresponding to a unit perturbation. So unit perturbation here means that since the unit of our electrostatic potential is just voltage, so it is corresponding to 1 volt fluctuation. So we have to normalize it by 1 millivolt. That's the reason why I just draw the difference between these two cases and multiply 1000, because 1000 is just the inverse of 1 millivolt. Of course, if we have 10 millivolt spacing, then I have to use this 10 millivolt spacing. Then my weighting factor or multiplication factor should be instead of 100. Okay, so now and please have a look at those results. Please try to make comparison between symbols and your line. How do you feel about their comparison? So they seem to be quite similar and they agree well. It means that, okay, although we have used simplified approximation for smallness of our perturbation, however, under that assumption, actually that is corresponding to the finite difference of our system. We manually calculate the one solution and another solution and take the difference, but that is really corresponding to the simple linearized system. Of course, this is possible because we have used small difference. For example, instead of that, I just used 0.6 volt and just multiply 10. Then what will happen? So if this is not very obvious to you, then how about this one? I just apply 1.5 and take the difference and just draw something. Of course, you can find that you can say 0.5 and 1.5. The midpoint is no longer corresponding to 0.5. Okay, then how about this? I just calculate the equilibrium solution and 1.0 volt solution and take the difference and say that this is corresponding to the small signal uh, analysis to 0.5 volt. So can you understand? It's can you accept this kind of approximation? Certainly not, because here between 0 volt and 1.0 volt, the difference 1 volt is too large, so it just change our system response too severely, so we cannot use any further the linear approximation or smallness of our perturbation. So please use this technique for appropriate cases only. In the previous slide, we have shown delta phi. And now we are now looking at delta n and delta p. And this one gives you also another comparison. So once again, symbols are obtained from the same setting. So I mean that taking the difference between 0.5 and 0.501 volt and multiply 1000. These symbols are obtained by that way, finite difference, and line is obtained from our small signal analysis. You can find that, okay, they look quite similar, so good. And another one is this is corresponding to your electrons. So this is corresponding to your delta n, and this red colored line is corresponding to delta p of your holes. So what does it mean? What it means is when you apply the additional positive bias to your anode, then you just collect certain electrons nearby the depletion layer. Also, at the same time, you collect the similar amount of positive charge holes in your depletion layer. So, what is it? You know that in this case, depletion layer exists, and in this layer we have no electron and we have no hole. However, by applying additional positive voltage, we can collect more electrons in no electron zone and also collect more holes in no hole zone. So what is it? It simply means that now depletion layer, its width is now reducing. So depletion width is now reduced. Why do we have this reduction of depletion layer width? This is simple because compared with 0.5 volt, 0.501 volt, this is more forward bias. Since forward bias is applied, then depletion layer should be reduced or shortened. That is well reproduced, that physical expectation is well reproduced by our simulation. So of course, if we okay, so that is the thing we have to understand. So looks quite okay. Then let's go to the one like response of terminal current. In a similar way, we can calculate the terminal current, for example, the anode current, and it is given by certain number. What is this number? You easily understand this is related with something. So if you remember, so your diode anode current is simply given by this one, your dark current times exponential your anode voltage minus Vt divided by Vt. Here you have actually certain number, usually called as n or something, but here you have a certain number called as ideality factor. So in reality, its value seems to be around 1 and 2, but you know, in our PN junction, we have no additional physical effect, so this ideality factor should be 1. So we are now considering very idealized case. So what you can expect from this simple expression is, wow, when we calculate di anode over dv anode, that will be simply I dark times 1 over Vt exponential V anode over Vt. Then you know that this is almost identical to the anode current itself, because here, although we have here -1 factor, however this -1 doesn't make any sense because this exponential function gives you really very large number. So that is simply given by I anode divided by Vt, thermal voltage. That is expected behavior of your di over dv. Then my question is, we have obtained di over dv given as this number. 누구시죠?
교수님 시설 교수 나왔습니다.
네, 수업 중인데요.
예, 알겠습니다.
네. Okay, so this is the dv over di, but it means that this is corresponding to, if our exponential dependency is really true, then this is simply given by I divided by our summer voltage. So then can we justify this kind of observation? So now let's go to our previous one. Our previous example. So now you can see that here its DC value was just like this number. This is our anode current. and please divide it by our summer voltage. What is inverse summer voltage? Inverse summer voltage is roughly number 40 per volt. It will contribute. So you will have this 50, roughly 56 times nanovolt per nanoampere per volt. That will be the expected behavior of di over dv. And please have a look at this one. You can see that this is the case. So now you can see that my terminal current estimation is well done with this evaluation. And please note that also we can also try to make a finite difference. Once again, take the difference between these 2 points, then we can find a certain number. Well, it looks good. It just shows about just 2%, roughly 2% difference. But do you think that 2% difference in our calculation is acceptable or not? So to me, actually, it is a little bit uncomfortable because we are now comparing just the apple and apple. They are the same, so we wanted to have a better agreement. So instead of that, I have introduced a really small delta value. Then I have obtained much smaller error originated from this finite difference. Why do we have this kind of problem? Because when we have this one, actually its center point is no longer 0.5. Actually this is corresponding to this number, and this is small error like 0.5, and actually we are now considering 0.00. These small differences in the central central bias point introduce small error in our calculation. So are you with me? So that is one thing we can expect. So now let's go to the non-zero frequency. Okay, up to now I have shown you that using just this Jacobian matrix and changing the residue vector only, we can get the response of our system by small voltage perturbation. However, previously we have just applied extremely low frequency voltage excitation that doesn't generate frequency dependent phenomena. So today or from now on, we'll just show you the non-zero frequency excitation. Then what should we do? The modification from 0 Hz case is quite simple, amazingly simple. So because most of calculation has been already done in DC calculation, and frequency dependent terms should be added. For example, here we have the terms like the partial derivative of delta n. So now in this case that can be just converted into j omega delta n. Of course, you can have similar terms like j omega delta p. These terms should be included in your new system matrix. Of course, please note that this one is related with this imaginary number. So now your A matrix is no longer a real matrix. It is now a complex matrix. So please adjust your code to adopt this kind of complex matrix. So if you are working with Python or MATLAB, actually that is not that difficult. And if you are working in the C++, then actually you have to find out a new driver and new data structure support the complex number and complex matrix. But I hope that nowadays it is not that difficult compared with 20 years ago. So now you can anyhow manage it. And I think that that's it for calculating the solution. However, one caution is when you calculate the terminal current, you must consider displacement current. So please note that previously, even for transient simulation, you have considered displacement current. So therefore, you must also consider it. I mean that the form of sorry about that. The form of displacement current is simply given by this form. Yes. So this is the original form, and it will convert it into j omega times delta d. What is delta d? Since d is given by epsilon d phi over dx and minus, so actually delta d should be written as this form, right? Delta phi. Oh, yes, that is the form we must have. So please implement this form, and of course with the j omega term, then that will give you the displacement current term. That is quite important. Without this term, you cannot get the correct behavior of your system. Then I think that now we are going to the almost last slide of our lecture in this semester. Then let's consider relatively low frequency like 1 megahertz. So here now your solution has real part and imaginary part because everything is now a complex number. So you have delta phi, but you can take the real of delta phi and you can find imaginary of delta phi. They are drawn in this slide. So you can see that the real part looks quite similar with our previous one. Yes, here we have positive 1 and number 0 for anode contact and cathode contact, and in between we have change of potential. Yes, this is nothing new. However, when you have a look at the right figure, then you can see that imaginary part shows some behavior. And boundary condition, yes, here we have just 0 and just 0. In cathode, it's not that difficult to understand this one. However, even for our anode, we have applied just sine-like behavior. So this one describes cosine-like behavior of our electrostatic potential, and in this case there is no cosine-like term. So that's the reason why we have no uh, imaginary part of our electrostatic potential perturbation, and inside it we have some not that much intuitive uh, profile. And now let's go to 100 times higher frequency. Now we have 100 megahertz, but even in this case, we cannot see much difference in our real part. So even this 100 megahertz is not high enough to change its real part. So if you just apply the sine signal, then following the real part of your electrostatic potential, then there will be also just this-like behavior of your real part. But point is, here we have same imaginary part. This is imaginary part of your delta phi. And although sorry about this small font because I tried, but that was the thing I can do. Here you have a 0.0000025 compared with the previous number like 2.5 times 10 to the minus 7. That was 2.5 10 to the minus 7, and it is now 2.5 times 10 to the minus 5. What is the difference? This is exactly 100 times. So this imaginary part is generated from your j omega term. So since j omega itself is increased by factor of 100, so your imaginary potential is also increased by a factor of 100. Now you can understand. And I think that this is the real last slide of in this semester. So I have implemented the terminal current and changed the frequency from 100 kilohertz up to 1 gigahertz, and just drawn the real part of our anode current and imaginary part of our anode current. So how does it look like? So we have changed the frequency 4 orders of magnitude, and you can see that this real part called as conductance seems to be almost close to a constant. Of course here we have a slight increase, so beyond this frequency, beyond the gigahertz range, then we will have a very dynamic behavior of both of real part and imaginary part, but at least below 1 gigahertz signal. So now you can see that here we have almost constant value of our real part. And how does it look like? This one is just linearly increasing. So is it really linear or not? Please try to draw this graph. Here we have one number 10 to the minus 8, and this is corresponding to 10 to the minus 9. And here we have a 10 to the 5, 10 to the 6, 10 to the, and this line, what is it? If your input is increased by a factor of 10, your output is also increased by a factor of 10. This graph shows the linear dependence between your current and your frequency. And please have a look at your imaginary part. How does it look like? It exactly follows the linear dependence. So simply speaking, your current, your delta I, can be written as certain number like so let me just try to read it. 10 to the minus 8, 1 2 3 4 5 something, yes, roughly 5 times 10 to the minus 8 plus, what is it? Here we have a certain number, and this is really imaginary, and we have something proportional to your frequency. Here you have a certain number, so I have no idea about that, but that will be the case for your calculation. So of course you can roughly estimate it, because when you have 10 to the minus 10 to the 7, then your admittance just looks like 10 to the minus 7, so it will be roughly 10 to the minus 14. So then when you apply, for example, 10 to the 9, you will have the quantity close to 10 to the minus 5. So anyway, that will give you this kind of number. So now you can actually interpret these two components. What is it? This small signal component, this is just can be interpreted as a inverse of a certain resistance. Here we can interpret as a certain resistance R, and here also we can see that there is another conduction path which is proportional to the omega or frequency that is corresponding to our capacitance C. So now you can easily understand the behavior of our PN junction bias at 0.5 can be understood as this form. This real part through R is described by this real part, and the imaginary part describes the curved path through the capacitive component. So your IC modeling can be done after you extract this kind of admittance. So you can do it. Okay, so this is the end of my prepared slide. So then now let's review our entire semester. Well, uh, uh, this course is a new course. I have opened this or provided this course for several years. However, in this semester, we have something new. Something new was related with, most importantly, the process simulation. So at the very beginning of our semester, we have thought about process simulation, especially in this semester, diffusion simulation has been covered. So for considering that diffusion simulation, we have studied many techniques required for solving these TCAD problems. After that, we just go to the device simulation, starting from quantification and eventually go to the drift diffusion and Schapter-Kummer one. And another one, new feature. So the second feature is nothing new. That is the main body of our lecture. And eventually we considered the small signal analysis, which has been never considered in our previous semesters. So I think that in this semester we have covered two different but important, equally important topics. So thank you for joining this semester, and yes, so please be prepared for your final term project that will have the ultimate the decision for your final grade. Okay, please remember that due is not next Monday, but second next Monday. The second next Monday is the due date for your final term project presentation. Please send me your recorded video. Then based upon your the quality of your video, I will make the evaluation. Okay, do you have any question? Okay, if you don't have any questions, then I want to wrap up this semester. Thank you for your effort. Bye.